Hello guys, today we are going to discuss local backlink concepts, which is actually applicable for Stiffened and unstiffened element for different sectional shapes uh, in steel. So for the consideration of our uh, stresses and area, we consider now two types of element. First one is the stiffened element, okay, wherein the edges of the element itself are assumed to be restrained, no? Uh, Assuming that these are supported on the edges by either hinge or fixed support, there will arise a symmetric but non-uniform distribution of your stresses. So for this particular stress distribution, so this is a non okay uniform uh, but symmetrical, no? Symmetrically placed stress on on the stiffened element itself. So to simplify this stress distribution, we assume that uh, this uh, non-uniform stress is concentrated on an area, which is what you call the effective area or simply the effective width. In this case, these are coming from the edges up to very near the mid of your plate element, thereby assuming that the total force induced in this system is actually equivalent to the force induced in this system by way of uh, assuming a uniform distribution but reducing the width of the plate element to what you call an effective width. So in both sides, the effective width now is simply one half of the total effective width. So for this consideration, we can uh, derive the formula on the shape factor later, no? For a stiffened element, wherein the concept that was used is what you call the effective width concept. So assuming that your total actual strength Pn is simply equal to your effective area, which is simply the thickness. Okay, so the thickness of your uh, element multiplied by the effective width. Okay, so we come up with what you call the effective area. So the effective area now multiplied by the maximum uh, stress considered as uniform will now be simply equal to your actual load Pn, or in short, this is simply equal to A effective multiplied by F max. To derive a formula to represent the shape factor for the stiffened element, so we simply divide this uh, product here with A gross and multiply it on top. Hence, we now define a variable QAs representing the shape factor for stiffened element, equivalent to A effective all over A gross. Okay, so your value now for the load will simply be reduced to a stress multiplied by the area formula, and with, of course, the inclusion of a shape factor that will reduce, okay, the amount of your actual load. Always QA must be less than or equal to 1.0 here. So for the unstiffened element concept, we now consider this figure here wherein the support are no longer support are no longer symmetrical, such that your edge here is restrained while the other is free. Hence, a again a non-uniform distribution of moment will exist, but the difference between the first and the second one is that the first one here is symmetrically placed. Okay, so this is uh, symmetric because the support condition are the same on both sides, while this is non-symmetric. Okay, uh, where the side having a restraint condition gives you a bigger stress. So the stiffer the edge, the bigger the stress it will absorb. So this non-uniform can actually be approximated by taking, okay, an average stress, F average, and multiply it by simply the total width of the member or the plate and the thickness. So your derivation for such will be uh, represented by this formula here, where the nominal actual load is simply equal to the uh, area gross. So this is now the gross area multiplied by the F average. And this gross area, this F average can actually be divided by the F max to make it consistent with the first one. And multiplying it again by F max makes this ratio defined to be your QS shape factor. So this is now the shape factor for your unstiffened element. So the formula now is reduced to Pn is equal to Qs times Fmax times A gross. So take note that for sections and shapes with both stiffened and unstiffened element, the compression system should be treated as unstiffened for establishing the stress. Hence, the F that we are going to multiply with the area will be the F average, so that your Pn now becomes, okay, so for this is the third scenario, so the A effective times the F average, where this can be divided by the A gross and multiplied by the A gross, so you didn't do anything because this is simply equal to 1, and the F average is multiplied by F max divided by F max, taking note that these two ratio here are simply the shape factors QA and QS, where Q is simply the product of QA, the stiffened, and QS, the unstiffened, multiplied by A gross times F max. So this is the formula you are going to use for your actual load capacity whenever there is local buckling present in your member. So for the values of QS for slenderness and stiffened element, we refer to NSCP 505.7.1 or simply your AISC reference with this formula. So there are actually 1, 2, and 3, 4 cases no? Involved depending on the type of unstiffened element that you are going to compute. So later on we will be solving problems concerning this. So for flanges, angles, and plates projected from rolled columns or other compression members. For example, I have here a rolled I shape. So we're referring here to projected. When you say projected, this is actually okay, the plate element in question. Okay, so this is now the flange of this rolled shape, used normally for columns and other compression members. Okay, so for angles and plates projecting from rolled shapes, which means that if this is if the compression member is made up of, let's say, an angle bar like this, so you can also consider such projection such projection a case of number 1. So this is now my projected element. So these are my unstiffened element. Okay. Okay, for the number 2 consideration, this is now for built-up section. So if the first one is concerned on roll shapes, so we are now concerned here for built-up sections. So for this is welded here. Okay, so this is now your projected unstiffened element. Okay, so you can also make use of other sections using angle shapes, other shapes or plates, projections, let's say for T's, no? So we have here your T section. So this is also considered in this number 2 case, no? and so on and so forth. So all flanges projecting from built-up sections. Another example maybe is to have a road shape. Let's say you have here a road shape. Uh, but this time you are not concerned with this flange, but you have a plate here placed or welded. Okay, so this is actually a projection. Okay, so this is welded there. This can be considered a projection, a plate projection on this built-up shape. Okay, so take note that we are now concerned with this plate, not the uh, flange of this road shape here, because this is very stiff already upon adding an element on top of it. Okay, for case 3, we refer to single angles. Okay, for single angles, so it can be, uh, these are rolled shapes, of course. It can also be a single angle composed of a plate element. Okay, so whether it is rolled or built up, you can use this as a single angle. Okay, for stems of T's, we are referring to any, again, any shape of T, so the stem is this one. Okay, so this is the stem of T. Okay, for the values of effective width, BE, for slender stiffened element, which are used to determine the value of your QA, the formula is actually enumerated here. We have actually 3 cases again. Okay, we have the uniformly compressed slender elements for rectangular sections of uniform thickness. So we normally have this is your stiffened element. So you're referring here uniformly compressed. Okay, for flanges of square and rectangular sections, you are referring to shapes like a box shape. Okay, so these are now your stiffened element. Okay, and for the last, we have the circular shape. So for a circular section, this is also a stiffened element. Okay, so what is now your uh, d over t? So your diameter outside, okay, sorry, outside diameter d is the one that is referred to here, and your thickness simply this one. Okay, for the nominal compressive strength, Pn, it shall be determined based on the limit states considering flexural, torsional, and flexural torsional buckling. Okay, so I have here a sample MathCAD plot of the QS equation for FAP projecting from rolled shape. So this is actually case 1. Okay, so this is case 1. So I just did this for your reference. If you want to make a program to define your QS value automatically, so you just use this. Okay, so this is on the basis of comparing your lambda, okay, your lambda s or lambda uh, of the unstiffened. Okay, by the way, class, take note that the letter S there means unstiffened. So the subscript for stiffened is A. So for lambda A, you are talking of stiffened values. Okay, so your lambda S is simply the width B over 2, okay, divided by the thickness of the flange. Okay, so we are referring here for F means flange, A means angle, P means plates. Okay, so any rolled shape, or sorry, any flange, angle, and plates that projects from a rolled shape section is considered here, no, in this particular definition. Okay, so your lambda r value is 0.56 square root of E over Fy as defined from your table. And if it is less than, if lambda s is less than lambda r, then your QS is simply equal to 1.0, meaning to say this is not slender. Okay, so if it is greater than lambda sub r but less than 1.03 square root of E over Fy, then it is uh, what? Partially slender. Okay, and then if it is greater than 1.03 square root of E over Fy, then it is slender. Okay, so this is how you deal with the formula, and the value of QS changes from 1, okay, to this and to this. So the graph of this equation now is as program is represented by this value here. Okay, so all you need to get is your lambda s. If it falls here, then you just compute the graph. If it falls at 10 over 1, which is 10, okay, so you can see that it falls somewhere here, okay, which is 0.98. Okay, so this is a visual overview of what happens to your QS value when the lambda s increases. Okay, so you can also do it for case 2 scenario, and take note that the shape is not changed, no? So the shape is actually still the same, uh, but the values are not exactly the same. The shape is the one that's important, no? To interpret what happens as your lambda s increases. Again, this program is just used to help you find easily what the value of QS is by means of this program here. Okay, so that's all for uh, the computation for QA and QS. So we'll apply this formula later when we solve problems on local buckling behavior. Thank you very much.